Hi, everybody. My name is Sergey Weber. I will host the next session. Um, Welcome, everyone, also to the second keynote of this day. In the next session, the second keynote is all about pushing the boundaries in automotive cybersecurity. With me, I have Ahmad Nasser. He will be presenting the following topic: Rising the Cybersecurity Bar, Seeking Unconventional Methods to Solve Conventional Problems. He will address the critical challenges in securing software-defined vehicles from three points of view: technical, compliance, and a human perspective. Ahmed will also talk about how generative AI can enhance cybersecurity efforts and help us to stay ahead of threats. So let's give a warm welcome to Dr. Ahmad Nasser. The stage is yours.
Thank you, Sergey. Thank you so much. Okay, so this is Ahmad Nasser. I am the lead security architect of DriveOS, which is NVIDIA's autonomous driving platform. And I will be presenting today on this topic of raising the cybersecurity bar. So as Sergey mentioned, in this talk, I will start from the perspective of DriveOS and the lessons we learned from developing this central compute platform. And what are the unique aspects for software-defined vehicles in terms of cybersecurity. Then I will touch upon the various challenges along process aspects, human aspects, and technical aspects. And finally, I will share with you some success stories for applying generative AI to address some of those challenges. So I think by now we have all heard enough or we're pretty well familiar with software-defined vehicles. We know the challenges. I think there were several talks about the topic. So from our perspective, we just like to share some points about what we have observed since we are developing in this space. So first, I'd like to say that the transition to software-defined vehicles is really a giant leap forward for the auto industry. The OEMs that have engaged in this effort and are either in the process of building these vehicles or deploying them, they have really had to do significant changes in their process and their development efforts and how they produce software, how they develop it, and so on. So unlike the traditional architectures where each ECU has its own processing unit networked via CAN, separated into domains, software-defined vehicles are using centralized computing platforms. So these allow us to consolidate vehicle functions, typically in virtual machines. They're typically communicating via shared memory protocol between these applications. So this allows for a trend of hyper-consolidation of functions into the central compute units. And because of the ability to do that, we end up with a culture of acting fast, reacting fast, and failing fast. So these systems can be updated frequently. They can have new features. And when things are not working, we have a way to pivot and try something different. But all this whole dynamic creates a lot of pressure on executing the secure lifecycle management, because you have to now do all the process work within this dynamic environment. So what we observe is there's a constant need to balance the innovation required for developing these advanced systems with the expectations of functional safety and cybersecurity. And I hope to share more stories about this throughout this presentation. So throughout this whole process, we still need to maintain the security posture. We really cannot waver on the cybersecurity and the safety of these systems if we are going to have a future for SDVs. So why do I bring up DriveOS, and what does it have to do with this story? So DriveOS is simply NVIDIA's software platform that runs on the NVIDIA chip Tegra. Right now, Orin, and the next version is Thor. It's already in development. So DriveOS is simply a software platform that enables multi-domain compute. So rather than having these domains being separate ECUs, they can now be executed on a single chip, single software platform. We can have ADAS, AI companions, instrument cluster, gateway, all on a single chip. And this is only possible because of the capabilities of the hardware and also the technology that we have in the software. So a brief word about DriveOS. It's really designed from the ground up as a central computing platform. It runs on a high-performance compute device, like I said, the Tegra chip. And these systems have to have a rich OS. It's either Linux or QNX. And there are multiple safety qualified RTOS instances running on different cores, real-time cores. Uh, Obviously, there is a hypervisor that has to virtualize the hardware and spin up these virtual machines. And now there are many cores that are running specialized firmware. For example, the GPU has its own firmware core running firmware. There are inference engines, various hardware accelerators. So this type of architecture can support multiple virtual machines and virtualized partitions that can give you services needed across different domains. And naturally, this enables us to have mixed safety and security criticality software. So which is perfect for both functional safety and security. So these systems were designed for advanced AI inference, so things like computer vision, also graphics, rendering, audio, and various other use cases. And also, one feature of these systems is the need for advanced networking interfaces. So there's both Ethernet support as well as low overhead inter-process inter-VM communication. So what does DriveOS look like, and why really what does it really matter? So DriveOS, this is a block diagram that shows the various IPs that are in the chip. DriveOS is providing several drivers. There are about 30 elements. Elements are simply software components, and these elements range from the boot stack, the uh, the virtualization system software like the hypervisor, the various libraries, middleware, storage, handling, and so on. So it's really built on the concept of defense in depth and zero trust model. Uh, from the very beginning, DriveOS relies on multiple redundant boot chains with secure boot and trusted setup. So the system boots up into a secure state. If there's ever a problem with booting one boot chain, we have redundant chains that allow us to recover. The hypervisor is virtualizing and isolating resources. Then when we get deeper into the guest OS, we have a strict OS security policy that ensures least privilege is applied, and there is identity access management enforced. A trusted execution environment allows us to do critical operations like setting up the key store, and there is a key management and crypto stack that uses PKCS 11. Software update management is another component of this solution, and it's necessary because we all know we have to have constant updates and we have to do it in a secure fashion, which includes authenticating the packages that come in, checking compatibility, and so on. In addition to this, there is secure sensor protocols supported. For example, camera sensor authentication. All the camera frames, they have to come in, they get authenticated, and they are passed up to the application if they are passing authentication. In addition to this, there are secure networking protocols such as MACsec, and we cannot ignore also the debug and logging infrastructure, which I'll talk a little bit more about it, but that has to be secure, and we take many measures to ensure any backdoors are taken care of. So overall, this is kind of like in a nutshell what the defense in depth strategy of DriveOS is. So the mindset that drives this kind of development is really security vigilance mindset. So we take this approach of building defenses with the mindset that a safety impacting breach is imminent. This kind of idea is very important because people can fall into a sense of complacency. They may think, what's the likelihood of something bad happening? We don't want to take that kind of mindset. We actually want to think like really it can happen anytime. That's why uh, we build defenses with that mindset. Okay, so what are some of the unique aspects that we observed while developing DriveOS and while deploying it in various use cases. Some of these are quite obvious to many people, but I'll share them. It's a good refresher. So the first one is fast startup time. Even though these systems are quite complex, there is a huge number of sensors that have to be set up. Components, hardware components have to be initialized. Virtual machines have to be set up. Applications launched. Still, fast startup time is a requirement. And the fact that these systems rely on high-speed Ethernet as the backbone for in-vehicle communication, it always places a pressure on the crypto acceleration requirements. So you start noticing that, I need a lot of crypto accelerators. I need very efficient data handling of moving data between the crypto accelerators and memory and so on. And that given that many features within the SDV environment are rolled out without a hardware change, there is an expectation of constant feature updates. So the speed of development is quite fast, but that also means the attack surface is expanding quite fast. And we have to keep up with this growing attack surface and not even, like, we cannot stop paying attention to it. Another aspect of this architecture, which is unique, is the integration of edge computing capabilities and cloud services outside the vehicle. So this is something we didn't really used to worry about before when we developed normal ECUs, but uh, that that now adds the requirement of secure communication protocols, high bandwidth, and again the need for fast crypto acceleration. When it comes to integration and testing, these systems even are more challenging to integrate and test. And so when you start thinking about new security requirements that you enforce, for example, if you're tightening how the system can be debugged, or you're tightening what kind of logs you can capture, you can start noticing that it immediately has a trickle down effect on how the system is tested, how it's integrated, how it's deployed. So these are other things we have to pay attention to. And so the bottom line here is the complexity of these systems make it impossible to handle safety and security as an afterthought. I think we've been listening to the same story of secure by design, and it couldn't be more true in this case. I mean, it's true everywhere, but here it's really important. Okay, so now we talked about DriveOS, the experiences we gained from developing it, how it fits in the software-defined vehicle um, story. What are some of the challenges we observed, and what can we do about them? So I break up the challenges into three areas: the process challenges, and then the human challenges, and finally technical challenges. These are some challenges. Obviously, there are more. So the first one, obviously, it's the need to keep up with the fast execution cycle. Our process, or whatever security process we deploy, it needs to keep up with that fast execution cycle. So uh, if the process is slow and cumbersome, it really becomes the bottleneck. And engineers are very innovative, so they'll find ways to circumvent the process, and that's something we really try to avoid. So we have this difficulty of letting the process be as lean and efficient as possible to keep up. And another side effect, if the process is not lean and efficient, if it's not able to keep up, you can have the case where engineers fall into the trap of checkbox security. So they try to reduce the process into paperwork, or they try to, do the motions of the cybersecurity risk management, but not really reduce the risk significantly. And we try to avoid that. Now, the complexity of the software bill of materials, this is a topic we've heard numerous times. It's very well discussed. When it comes to these systems, it gets even more complex because the open source software that's included, it adds another dimension of difficulty for vulnerability management, because many of these open source libraries, for example, they were not designed for, maybe they don't have a security process. So who's going to own it? We find that we have to own many times we have to own that responsibility. And along the same lines, the supply chain contains many off-the-shelf components because these systems share many common features with enterprise systems and IT. You can have many components that were developed for non-automotive use cases coming into these systems. And we obviously, if we're developing with ISO 21434, we have to account for the off-the-shelf components. We have to account for all the cybersecurity gaps that they may have and do the work. So this again shifts the burden on the system integrators. And the final observation, it has to do with the maturity of the process. If the organization is still maturing in the space, we find that there is heavy weight on the right side of the V, or right side of the V model. So issues are discovered during verification. There's a lot of work done in reviews, in testing, but not sufficient work being done on the left side of the V. And what happens with this kind of process that is heavily weighted on the right side of the V, it ends up finding issues way too late. And because of these systems being very complex, it's really almost impossible to fix things if they're found extremely late. So that's another one. On the human resources challenges, the first one is the knowledge gap. So we have been discussing cybersecurity for over a decade in automotive, and I think numerous professionals have done significant work to reduce the knowledge gap, but it's still a problem. The automotive engineers are facing many stress factors. It's not only that they have to keep up with the new attack methods and new vulnerabilities and new ways these systems can be compromised. They also have to be retrained. Many of our engineers started developing for classic ECUs, so they're now having to learn to adapt for developing in service-oriented architectures, as opposed to RTOS-based architectures like tasks and so on. So this is placing pressure on the entire engineering workforce. And training the workforce is still a challenge because the dynamic nature of cybersecurity means you can't just go take a class like one time and come back and now you're good. Security is dynamic, so your training needs to be also dynamic. Another challenge on the human resources is something when I speak to many people, even in the industry, there's still a skepticism among engineers and managers about the need to really take decisions like delaying projects to address security concerns, because they in their mind, if for example there is a security risk that needs to be addressed, but it's going to cause a delay, for example, or it's going to cause a significant cost impact. They're thinking about something that's certain versus something that may be likely or may happen. So what's certain is that the schedule will slip. What's certain is that maybe the business will be jeopardized. But what's likely is maybe there will be an attack, maybe there won't be an attack. So this kind of mindset, it's very hard to battle. And we as security professionals have to be always able to explain the importance of addressing cybersecurity risks in a way that also does not derail a project schedule. Another aspect which we also find is there is a hard time for some engineers or many engineers to fully understand risks when it comes to complex attacks. So if something is complex, they may immediately think that it's not likely to occur. But in fact, complex attacks can still occur. Even if we have a hard time understanding them, that is not a reason for them not to happen. Which brings me to the next mindset, which is mindset for justifying complacency. Basically, just because we have a shortage or a deficiency in our imagination of how something can be attacked, it does not deter it from happening. And so we really have to be able to grasp that some things are possible and there always advances are happening in this space that it may look like it's very difficult for us to carry it out, but experienced attackers are able to do these things. Okay, the final aspect which I will touch upon is the technical challenges. And The first one, with the domain-driven E architecture, where we had multiple physical layers of separation, if it was architected properly, even though it's not a perfect security architecture, but it still offered significant challenges to attackers to reach the deeper layers of the E architecture. So if you had, for example, your body control, your chassis control buses, they're all separated by a gateway. There were multiple layers of penetration needed. If it was architected properly, the attackers had to go through several steps to get to the steering and braking and so on. But with the centralized compute platform, it's now possible to have the vehicle control software one hop away from external networking software. And this is all dependent on how the OEM designs their system. But for example, let's think about the worst case scenario. If somebody were to design a system with everything in a single virtual machine, you'd have your driving control, your networking stack, your Wi-Fi, your Bluetooth, everything in one space. This can be very challenging for holding the security bar. And so we need to strive for designing these systems as if we are emulating physically isolated compute instances. That's really the objective here. And yeah, that's one point. Uh, Another technical challenge has to do with the need for data-rich applications. So when we develop normal ECUs, we always needed diagnostics, calibration, and things like this. But with central compute platforms, there is vast amounts of data being transferred, not only in development but also in production. And there's a need for debug and troubleshooting and profiling, getting the timing performance and things like this. And if we don't properly pay attention to these, the way these things are implemented, we can end up with many useful backdoors for attackers to exploit. So that's an aspect that really has to be considered. Uh, as far as update capability, again, this is a topic that has been discussed numerous times. We have discussed OTA security, we have discussed OTA deployment. We all know it needs to happen, but we still see that pushing updates to millions of vehicles in a timely fashion is still a challenge, especially for safety critical software. Being able to go from a software change to an actual release is still a very long lead time because of all the effort needed for recertification and so on. And then the final technical challenge has to do with the backend servers. So this is an area that is not very well understood by everybody working in the domain and not always accounted for. So some people might imagine that the vehicle is kind of like an air-gapped island. It's kind of driving, but there's no threat against it. But it's constantly connected now to the backend, and we have to consider the threat of the backend itself. Okay, so we've talked about all the challenges. What about the attackers? What is their state of affairs? How are they doing? Are they doing better now with these architectures? Well, luckily for them, software-defined vehicles suffer from vulnerabilities that are common to IT systems and enterprise systems because of the shared kind of networking protocols and networking technologies that are there, the service-oriented architecture. So now attackers have a lower barrier to entry when attacking SDVs. They can leverage whatever tools they have developed, whatever expertise they have gained over the years to now apply it to these systems. Another advantage that attackers have is standardization. While it is desirable for us engineers, we're always striving for standardization. It's also very useful for them because now they have to just learn one standard protocol, one standard software architecture, for example, and they can now apply it everywhere. If they can reduce the amount of investment they have to do versus learning something proprietary and having to rediscover things every time they attack these systems. And while most attacks are incentivized by money, we still see that vehicle theft, um, doing cyber attacks to steal vehicles is still the primary kind of like story. But it's not hard to imagine how even safety impacting attacks can be monetized. So we have to be very vigilant about this. And the final point is we we unfortunately can develop a false sense of security if we mistaken the lack of a breach with being secure. So is it really that your system is highly secure, or is it that nobody has knocked on the door yet? And so uh, this is one thing I caution against, is not to let this false sense of security creep in. Okay, so we know all the issues, we know what attackers are doing. What do we really want to do about it? So, and I'm going to be very, frank here. Security is prohibitive. It adds high effort. It requires specialized expertise. Almost always there's an impact schedule. If you implement some secure feature, you are likely to disrupt a feature execution flow. You're going to hold something, you're going to stop something, and say, okay, this feature was great, but we have to consider the risks. And there's always almost a performance delay. We're adding security controls. They're going to delay how fast we can boot the system, how fast we can process the data after we authenticate frames, for example. And there's always an increased cost. At the same time, if we try to play catch up to attackers, we will become like adjacent industries where security patches and active exploits are just common news. It's constant battle, and you're really falling behind. So what's the wish list that I like to share with you here? I try to summarize it into 3 points. On the process side, we need to execute the secure engineering lifecycle efficiently and seamlessly to meet the constraints of SDV. So we need some kind of process that is very lean, very efficient, and seamlessly integrated with the development process. It shouldn't feel like a huge burden. On the human resources side, we need to provide the workforce with continuous support and training. We need to make them feel and realize that security is not, not extremely hindering to them. Actually, we need to reduce the engineering overhead. And finally, on the technical side, we need to build secure architectures and secure code where weaknesses are identified and treated at design and implementation time, not after things have been deployed, not after things are already, for example, in the test phase. We need to find it when it's happening, when it's being introduced. So when it comes to SDVs, we all know we don't only need to meet the security bar, we actually need to raise it. But how can we do that? Okay, that brings me to the final part of this presentation. Can generative AI really help in this space? So we started with this kind of exploration about a year and a half ago because we had a real problem with our resources. We were short-staffed. We actually lost a member of our team that was highly experienced, and so we were wondering, what can AI do for us? So from the very beginning, we knew that not all problems will be solved by AI, but we start with asking the question of which problems are suitable for AI to solve. And we had this vision that security needs to become as seamlessly integrated with our development process as possible through the use of AI assistants and agents. We want to let AI do the busy work that we currently have no resources to do. And so this is what I'd like to share with you in the next few slides. All right. So before I go through the various use cases, the success stories, I'm just going to give a very brief review on what generative AI does for us in the security space. Some of you might already know this, I hope, but this is going to be very simplified. So I'm sorry if it's too simplified, but if we ask the question of what is security work, security work can be broken down into maybe 3 main aspects. We have search, we have comprehension, we have generation. On the search side, a huge part of our work is finding information. As security professionals, we have to analyze system architecture, we have to analyze feature requests, we have to analyze risk description, security manuals, tons of data. And this type of work, it's very time consuming, and you can always miss stuff. So search is a big part of our work. Another part is comprehension, where part of what makes this job exciting is that you come in contact with many um, different domains. So you're not going to be the expert in each one of these domains, but you will have to learn about them very quickly, whether they're networking, whether they have to do with virtualization, uh, OS, boot, and so on. You have to learn these different domains. And so analysis is a big part of what we're doing. Summarization, you want to get the information very quickly. You cannot read so many documents just to get up to speed to a certain point. You're always looking for inconsistencies. You're looking for duplication. And finally, there's a lot of part of our work is generation. We are creating threat models, attack paths, security requirements, security test cases. So all of these kinds of activities, they are actually suitable for LLM. So on the search side, with embeddings, vector embeddings, and retrieval augmented generation systems, RAGs, we can take text, we can vectorize it, and we can do similarity searches that give us the closest similarity. So we can build systems where it's much easier to find information than it used to be before. When I'm looking for requirements, for example, before I write a requirement, I can quickly find out, instead of reading 300 requirements, I can quickly find out just by describing what the requirement is. It's a semantic search. It's not a keyword-based search. When it comes to comprehension, obviously with LLMs, we can do analysis, we can do summarization, and again with generation, we can generate security work products. We can actually generate using zero shot and few shot learning. So I will show how we did that in the next few cases. So V model, we all know, we all have benefited from the V model. It has served us really well. It continues to help us build high quality software, but it's time to think about an AI augmented V model, a V model that AI. So which areas of the security overlay over the V model uh, can be implemented with AI? We found out that Tara completion and consistency checking, that was a very useful use case. Requirement generation and search, security requirements basically, specifically. Security weakness detection throughout the software architecture. So we actually can analyze architecture documents, sequence diagrams, and so on to find weaknesses. Secure coding rule violation detection and coaching. So this is about uh, being able to, first of all, understand what the rule violation is, understand what is the potential solution, and maybe even get the solution. Fuzz testing. It used to take so much time to generate fuzz testing test cases, but it's quite possible to auto-generate fuzz tests and actually get smart fuzzers out of AI. It's the same thing with unit testing. Automated continuous security reviews, rather than doing the manual security reviews that are very costly, very time, you know, they waste a lot of time. It's possible to do these continuous security reviews. And final point is mining past security analysis. So every time we do security analysis of problems, this knowledge could be useful for future cases, and it doesn't have to be dormant. It can now be mined. So when it comes to the Tara assistant, the first use case I will share, uh, our goal was to remove the monotony of Tara creation and make it more streamlined, make it faster. So if you have done a Tara before, you know that it can feel quite monotonous. If I'm reviewing the Tara, sometimes I'll find out that somebody wrote some threads and they did a few threads and they stopped. And I ask, okay, why isn't it complete? And they just say, well, it took forever and I had to do my other job. So we needed a solution that takes away this kind of monotony and let the engineer do the thinking about what is the risk and describe the risk in their layman terms. So the security engineer is describing a risk. They can say, okay, the system is exposed to this risk, and the worst case scenario can be this. The attacker will do it this way. And then the AI assistant actually can do the work of extracting the asset property, writing the threat description in a consistent manner, deriving an attack path, and writing a local damage, just trying to guess what the local damage can be to the component. Using the Tara assistant, we can then search through system damages. And because we have a library of system damages, at least for our system, we can try to do a closest match. So we can say, this is the local damage, this is the system damage. And once we find a match, we automatically inherit the impact rating from that match. So there's no need for you to rewrite, to re-evaluate the impact. And then we coach the LLM on what the attack feasibility metrics are. How do you decide if something requires a proficient or layman or expert and so on? And then the LLM can rate the attack feasibility, but also provide the rationale, because you as a human need to be able to judge whether the feasibility rating is accurate or not, and you can tweak it after. And obviously the full score is automatically calculated once all the variables are in. That's just a formula. And then the security engineer reviews the output, decides on the risk treatment, and can decide, okay, I will reduce the risk, I will share the risk, and so on. So the AI assistant can carry on. This is kind of like an agent where it doesn't stop here. It can find a matching security requirement. Maybe this threat has already been mitigated through a control, and we don't have to define a new security requirement. So it can find a match from a requirement database. And similarly, if there is a risk being shared, it can try to find the closest claim that already exists. We don't have to write a new claim. And if there's a need for a new claim, we can actually generate the claim from layman language. You describe the risk that is being transferred, and the LLM will generate it in formal language so that the time to review that is not that high. So this is the workflow. We start by the risk description by the user. The LLM using few-shot learning, which has examples of what's expected, can deconstruct the risk description into an asset, property, threat description, attack path, and the local damage. The local damage then is fed through a RAG search to find the system damage that's closest to match, and that actually affects the impact rating inheritance. The other parts are then fed again with the LLM prompt to get the attack feasibility rating and the rationale. So it looks like something like this. The user is given a window here, and it says, okay, describe the security story you are analyzing by stating the risk impacting an object within the system, how the risk can be realized, what is the potential impact, and it gives an example. So in this case, we show an example where the engineer was worried that there are power control APIs that can be manipulated by malicious application in the same guest OS. So this is cut off, but basically they were thinking that, okay, if somebody can do this, then we can have a disruption, unsafe control of the hardware resources. And so they write it down in layman language. What happens is the AI assistant now takes this and creates a new entry that's completely automatically generated, where it breaks up the asset property, threat description, even provides a recommended mitigation, and does the matching with the damage scenario, populates the metrics for attack feasibility, and then is giving the actual rationale. I know it's hard to see here, but it's giving rationale for why the expertise, for example, is expert, and so on. And this is not where the work ends. So the engineer is supposed to come, review this, and if they disagree with any part of it, they can change the ratings, or they can change a part, for example, the asset description and so on. So when we're done with the Tara output is fed into the security requirement generator. So this used to take tremendous amount of time. How do you generate security requirements? Security requirements are easy to say in layman terms sometimes, but really, if you want to write something that is meeting a guide of being atomic, being following a specific format, and also not redundant with other requirements, it's actually much harder than you think. So we took the output of the Tara, and we say, okay, you define a security objective that you want to achieve. and you define the feature, the source feature that um, was the source of the risk. So these are the two inputs that the security requirement generator takes. From that point, the program is going to search through the database of objectives and requirements. Because we've already written so many security requirements and we have their corresponding objectives, we can do a close match. Let's say we pick the top 10, and we can construct a dynamic prompt. This is a prompt that the LLM can use to generate the next requirement. So the LLM gets now a very good prompt that says, for this objective, we had this requirement. For this objective, we had this requirement. Here's a new objective. What is the requirement? And it's now able to write a requirement that's very close to what a human would write. Once that's done, there's actually a feedback loop. So we want the LLM to check its own work and do a check against a guide, because sometimes like the generated requirement is not going to match our guide completely. So the LLM will run another iteration, and whatever findings it has, it will now have a chance to fix it because there's a feedback loop. And similarly, the process continues. There are verification criteria that get generated in the same way. And again, they get checked against a guide. And what this does, this whole flow, it really eliminates a lot of the issues we used to have with the reviews. So our reviews were very lengthy, and we had people, give many feedback comments. You didn't follow the guide. This requirement is already inconsistent, or it's duplicating another requirement. So this has eliminated many of these issues. And obviously the human has to decide on the final modification, and then the actual human review starts. So that's still needed. Now we switch to the architecture weakness detection. So this is a problem that we essentially had due to the large amount of architecture documentation we have. It's actually not a problem, it's great. The more documentation you have, the better your analysis is. But we really literally have hundreds of pages of documentation about sequence diagrams, functionalities, traceability tables to requirements. And so we realized that we can leverage these traceability trees because of the fact that by the process, we have to have traceability between requirements, architecture, design, and test cases. We can leverage all this information to do deterministic searches for weaknesses. So we can build a database of all the text related to the requirements, the architecture, sequence diagrams, and then we can apply prompts that look for weaknesses, for example, from the MITRE database. So instead of having manual checklists, we translate these checks into LLM prompts, which are performed to assess the impact of the change. So this is, in a nutshell, we take a list of CWEs, we convert them into prompts, and we can apply them over a database. The database itself contains all the requirements, the architecture fragments, and there's an agent. The agent has, if you're not familiar with agents, I highly recommend that you read about LLM agents. The agent has tools at its disposal. So when it gets a prompt, it knows what it can do. For example, it knows I need to search for a requirement, or I need to search for the sequence diagram. I need to understand the sequence diagram. So these tools, it expand its abilities. And then it can go through this list sequentially, or it can do it overnight, and it generate a report of issues, and also propose fixes. So this is an example prompt to deal with CWE 657, violation of secure design principles. And so the LLM will be given this prompt, the agent will be given this prompt to look for problem areas along these lines when analyzing a specific part of the architecture. And so I'm going to show a demo, because I've been talking for a long time, and I'm sure you are curious. So this is an example demo of how the agent works. And this is the sequence diagram it's analyzing. This is a use case in which during the update management, after the update is done over the air, the application can request marking a boot chain as bootable. So now it says everything is done. Please mark it bootable. So next time we boot into this new boot chain. And so the software is supposed to check, for example, was the authentication done? Was compatibility done? And then finally mark it as bootable. So the agent is going to help us to find if there are any security weaknesses with this design. And so uh, the agent starts by telling us what it can do. And then the engineer says, okay, I want you to look up the sequence diagrams and dependencies associated with this functionality, analyze the diagrams, and verify appropriate access permission checks and partition validation checks are in place. And then we give it a guideline. We say if operations that happen across entities, like basically if it's one process to another process, should either include an access permission check or follow a successful permission check. And then I want you to list the checks that exist, so the good things you found, and the ones that don't exist. And also provide me the UML code if needed to add the check. So now the agent, when it runs, it starts making function calls. It says, okay, let me find this functionality first in the database. And then it's gonna, I guess it found another functionality, and then it's doing it, sorry. Okay. I skipped too fast. Okay, so it did a rag function to find more information about this functionality. And let's see, I'm gonna skip over because it's doing a lot of work. And it found the sequence diagram. It's actually calling a function to find the sequence diagram. And let's see if we get to the point where it gives the answer. So this was the outcome. It says, well, so it says these are the checks it found. There were access permission. Actually, it says the sequence diagram does not explicitly show any access permission checks. And then for partition validation checks, it says it does include a check. So it gave us what existed, what was missing, and it even suggested the UML code. So here we can see it's going to give the actual sequence diagram code. And let me see if I get to the final one. Okay, so finally the conclusion was the permission checks were missing, and I added the updated sequence diagram and the partition validation check while that was present. So there's no impact needed. So this type of agent, it can run in sort of like an overnight test environment. So it can run continuously because the architecture is huge and there are many checks that have to happen. Okay. The next one, and I think I have two more. The next one is the SAST assistant. So a problem we used to have is when you run static code checks, we get many warnings, many rule violations, and the engineers did not always understand what these warnings were. They did not understand them sometimes, and they didn't know how to fix them sometimes. So the SAST tool checker, it allows the engineer to pick a specific rule that was violated after they ran their SAST tool, and it will then obtain the violation, it will extract the rule, and then it will invoke the LLM to understand the rule and then suggest a fix. Once the fix is suggested, it will actually push a merge request into the repo for review. So this is an example where the code on the left had a integer overflow problem where the integer was being incremented without any check of the boundary. And after the rule was discovered, the SAST rule was in 30C. The LLM did the work of analyzing the rule, and it said the reason for this violation is because the unsigned integer can overflow when incremented. And then it suggested the fix. It involves checking the num output status are less than the maximum value before you increment. So you can see here, it actually, again, I misclicked. If the num output is less than the max, then it increments only. So what happens is the human now comes and has to do the human code review. And if they actually accept this, then it gets merged in the main line. Otherwise, it's rejected. So this cut down the effort significantly on understanding rule violations and also fixing them. So we come to the end. We have seen many success stories, but the bottom line is central compute architectures are here to stay. They are a key enabler for software-defined vehicles. But these architectures, they do bring some very unique challenges for cybersecurity. Along the process, along the human aspects, along the technical aspects, they do bring many challenges. And Gen AI is not only able to help us in meeting the security bar, it's really helping us to raise it. And the way it's doing that is by finally allowing us to have seamless integration of security work products within the V cycle so that we really can keep up with the feature and speed-hungry development of SDVs. These two things of security and feature richness do not have to be exclusive. They can really coexist. Second, bridging the workforce gap by providing engineers with the assistance and the agents is really possible. These systems can guide and aid in work product creation so that the engineers don't feel extremely overwhelmed. They have, they really have some help now. So the use of AI agents allows us both producing and verifying the security work products to give the human high quality output. So we don't have to keep making the human mistakes about writing things the wrong way, writing something as an attack path when in fact it's for example a damage scenario. We can get rid of these silly mistakes. And as we reduce the effort impact on the development cycle, we really are taking away the incentive to compromise on security. There is no reason for somebody to find a shortcut anymore. Well, at least that's the hope. We're not there yet, but hopefully we're getting there. And we have a way to eliminate the psychological barrier by engineers who find security a tedious and daunting task. So again, we try to say you're not alone and you have some help. So where do we go from here? We really need to look at all aspects of the secure development lifecycle. Not only secure development lifecycle, we actually do the same thing for functional safety. What areas can be, we call them LLMized, where Gen AI can be used. We need to identify new workloads that can help. And we also need to focus on optimizing the AI output quality. We know the output quality is not always perfect. So we have to have ways to, first of all, measure the output quality and have ways to find out how to improve it. Feedback, agents, multi-agents. And then finally, we really need to free up engineering time to look at hard problems, such as optimizing performance, improving usability, without the need to lower product security. That's all I have. And I want to thank the few engineers at NVIDIA who shared their use cases. This is a team effort. There's a big team that does this, and I really appreciate all their inputs. Thank you so much.
Thank you, Ahmad. It was a great talk. It was a great insights, very practical. There are incredibly, there's so many questions in the chat. Some about tools, the reliability of your large language models, segmentation, the Tara. Somebody also provided a new product idea proposal for introducing a Tara assistant as a standalone product, and so on. I hope you take the time, all of you, to discuss, to mingle in the lobby right after the chat, right after the presentation. Go there, meet, connect, network. That's also part of the this very conference. And we will proceed in round about 10 minutes with a panel discussion on automotive privacy. The question is it the differentiator or pain in the neck? See you there.
Okay. Thank you.
Thanks, Ahmad.